one and look at the series expansion, I get this because the one cancels out, so I have this. But yeah, otherwise and then I can rewrite this as the sum n equals 0 to infinity of this contraption right here. So this is actually the nth term in a majorizing series for the sequence. Oh, hey, we just proved it's uniformly convergent. Yay. By the Weierstrass M test. And it remains to, what do I need to show? So it's a uniformly convergent series of continuous functions, which means that the limit function is itself continuous by the theorem we talked about, right? Because we know that a uniformly convergent series of continuous functions has a continuous limit function, among one thing. But more than that, we can calculate as such, y in the limit function is the limit of the sequence, right? But that's the limit of the, t, act n, yn, but that's equal to this, right? And check out what we need to do here. So the limit of a constant plus this integral is the constant plus the limit of the integral. And then my claim is that I can pull the limit inside by the uniform convergence of the sequence. There's a little bit of a sleight of hand here though, guys, because what I'm integrating is not the sequence directly. It's the defining function for the differential equation evaluated at u comma yn. So there's still there's a gap in this proof. We should prove that the sequence that's defined by f of u comma yn of u is a uniformly convergent sequence. Fortunately, I have not written up your next homework yet, so we'll do that there. Yes?
I was just going to guess.
Oh, man. Silence. Foul being. Not even anything interesting. Anyway, sorry. Yes?
Should I just say what I think?
Yeah, I mean, what else would you do?
I don't know. It seems like maybe we can just pretend that it's like when we prove it, just.
Oh, you're thinking about your homework. Oh, we'll get to that later. So because this is in fact a uniformly convergent sequence, which is going to be based on the assumed continuity of f and the proved uniform continuity of the sequence, which we've already done by the Weierstrass M test, we can in fact flip the order of the limit and the integration like such. And once we do that, using the usual continuity of f to bring the limit inside, we then have this, which then shows that in fact the limit is indeed a fixed point of the operator, which is to say that it solves the differential equation. And these arguments can be repeated on the other half from like a to t naught. All right. It remains to show the solution is unique. If you have it that's a solution, then we would also have this, right? And then if you look at the difference between the other solution and the one we already found, you'd have this is less than that, which would give you this. And if you take the limit, where that's the norm, and applying what we just derived, similar calculations will show you this, and ultimately that. And as n goes to infinity, this goes to 0, therefore we get a unique solution. I won't belabor the point. We've done this kind of already. So there you go. This is why, well, I say theorem here. Honestly, guys, this is a corollary. Truth be told, this is a corollary. Because this next theorem this is what we by and large use in the differential equations course, because predominantly we're interested in linear differential equations. Although the existence and uniqueness theorem we started with today, it applies for nonlinear. Like nonlinear differential equations, if the partial derivative of f with respect to y is non-zero, if it's, well, not non-zero, but if it's continuous at the point, right, then we can find a unique solution at that point. I thought we had to have non-zero derivative. Let me not chase that rabbit at the moment, but so I still haven't written your homework up yet. I can do it there. But, sorry, it's too much fun. If we have a matrix of continuous functions on the open interval, notice open interval here, AB. So we're talking about a matrix of continuous functions on an open interval AB. All right? And we have also a continuous vector of functions on the open interval A to B. All right? And suppose further that T naught's a point in AB. Then there exists a unique solution of the initial value problem. dr dt equals to A of t times R of t plus F of t, where R of t naught is R naught, for any choice of R naught. And the proof of this is actually quite simple. So suppose you've got a closed subinterval of the open interval AB. I'll just use A prime B prime for that. And you've got T naught's an element of A prime B prime. Well, what do we have? We have F, we can define F of t comma R to be A of t times R of t plus F of t. By construction, this is the product and the sum of continuous functions, which is once more continuous. All right? So this is a continuous function on the strip R prime, I'll call it R prime, which is A prime comma B prime cross Rn. Furthermore, if I use x1 through xn to denote the vector of, the coordinates of that second piece here, then partial f partial xi is partial xi of this, right? But there's no xi dependence here, so that drops out. And there's no xi dependence in the matrix by assumption, right? It's just a function time. So the only place the xi dependence appears is right there. And, well, this is just 0 unless we're in the ith spot where we get 1, because partial xi is 1. But that's the ith standard basis element. So this is the ith column of A. All right? So therefore, and we already know this is continuous. That's given. Every component function is continuous, therefore it's continuous. So f partial xi are continuous on the strip. Therefore, we're getting there, the previous condition. We're going to apply the previous theorem, right? Furthermore, as this, if we look at just the domain being the closed interval A prime B prime to R is continuous for each choice of ij, therefore we can bound them by mij, right? And then I can let L be 1 over n. You'll see the reason for the 1 over n in just a second. The maximum of these guys. And then if I was to look at the norm of the partial derivative, well, that's the norm of the ith column. But think about that. Man, I guess it matters which norm I'm using. But I guess I'm thinking one norm here at the moment. So if I think about this, it's got to be less than or equal to n times the maximum absolute value. Like there's a component in this column which has maximum absolute value with respect to t being from the A prime B prime interval. So I just made that, this is like the maximum of all possible components in the matrix. So that means that I can make this estimate. Now this might not be quite right if I use the Euclidean norm. So there may be a slight flaw in the proof right here, but I think it should be clear that such an estimate can be made. It should be fairly obvious to you that we can bound this with the information that we have, whether or not my details are quite exactly right here. So thus the partial derivatives are bounded for the strip, and by the previous theorem we find a unique solution to the initial value theorem on the closed interval A prime to B prime, right? But the thing is, A prime to B prime is an arbitrary closed interval, so that means that we have a solution everywhere on AB. Because you pick any point in AB, I can put B prime a little bit past that point, and I can put A prime wherever I want, and I'll have a solution that goes all the way out to there. So if you think about it, proving it on an arbitrary closed subinterval gives you a unique solution on the whole thing. I do feel like I might be using a gluing lemma there. I had a paragraph written about using a gluing lemma to glue things together. I could think about it a couple more hours maybe I don't know, but I think it's mostly right. So then, the cool thing is, if you prove that there exists a unique solution for a linear system, you automatically then get a unique solution for the nth order problem because they're connected through the reduction of order. See, if I have the nth order problem, like so, I can rewrite this as a system of n first order differential equations by making the following substitution. x1 equals to y, x2 is dy dt, x3 is d squared y dt squared, and so forth, right? The given differential equation in terms of the reduction of order becomes like this is going to be your dx dn dt, because the derivative of this is the nth derivative, right? And then the rest of these guys are just literally like that's x1, this is x2, this is x3. So in terms of my reduction of order substitution, the given differential equation becomes that. So you put this all together, you've got a system of n differential equations. Like so. And because we're given that the coefficient functions of the nth order problem are all continuous, this is a matrix of continuous functions. And as such, the theorem applies. We get a unique solution to the arbitrary initial value problem. But that initial value problem has everything we need to construct the solution to the nth order problem. Because we just make our initial condition vector to match the reduction of order. See, I just set r naught equal to y naught, yn minus 1, where those are the desired initial values of the function, its first derivative, its second derivative, all the way out to its n minus 1th derivative. And this is equal to that, which is by the theorem equal to this. And that's exactly what we want when you translate back into the reduction of order. So, but at the base of everything, it's just the Picard iteration and it's Banach's fixed point theorem. So, questions? So, I think that's about all I have to say about Nagel, Saff, and Snyder. What remains, I will show you something I wrote a couple years ago with a student. And so what we were interested is solving this existence and uniqueness problem for A calculus. So A calculus, I've talked to you guys some about before. I'm just going to run through this briefly and, we'll just let that be. But so A is a commutative algebra. It's an n-dimensional vector space. So it has a norm. And that norm plays together with the multiplication of the algebra in a not the greatest way. It's submultiplicative. So like the norm of x times y is less than or equal to like some constant m times the norm of x times the norm of y. So it doesn't have a multiplicative norm like complex. That makes everything ugly. So anyway, you can, it's true, yes. You can define a function from the Cartesian product, the m-fold Cartesian product of A, to be A differentiable if each of the component functions is A differentiable. And you can define partial derivatives with respect to like A calculus and the differential of a function of m A variables. It works like this, all right, where these are the ordinary A derivatives, ordinary partial derivatives of the function. Anyway, let me not belabor those points. I really want to focus more on the proof here. So this is the theorem. Let I be compact and star-shaped in A, and let R be equal to I cross AK. So this is a strip. Well, it's a star strip, because I is a star, but AK is the full thing. This is analogous to the strip we just looked at. And suppose F is a mapping from R to AK is A differentiable, and that the partial derivatives in the A sense are bounded by L for each point in the strip. And let that be a point in the strip. Then the initial value problem, dy dz equals to f of z comma y with y of z not equal to w naught, has a unique solution on I. How do you think I'm going to prove this? Well, I'm going to use a Picard iteration. I begin by setting up, and this is the integral in the A calculus, which is done with respect to the multiplication in the algebra. So it's a generalization of the complex integral for those of you who had complex. So I set up the iteration like that. The notation here, this is a line segment from z to z naught, all right? specifically, this is what that integral is. It's a vector of A integrals, actually, because it's like a vector of A calculus. So like this is a vector of A integrals. And once more, that trick we just did, right? We rewrite the nth thing as a y naught plus the series, the telescoping series like that. So if we can provide uniform convergence of this, we'll get uniform convergence of that. And yeah, so, all right, so I is compact. So that means that we can find an M which bounds this continuous function. And as such, and this is that estimate. So there's the analog of the ML theorem for complex analysis. There's a submultiplicative of a constant. I call it the Memel theorem of A calculus because the M sub A appears in addition to the ML of complex. But there it is. So we have that is less than that. And anyway, then past that point, we need a generalization of the mean value theorem to make further progress. And let's see here. So let me go on because our time is almost out. So here's the generalization of the mean value theorem we proved last class, that the norm of f of a plus h minus f of a is equal to the norm of h times the supremum of x on the line segment connecting a and a plus h. And this is the notation basically for the Jacobian of f in this context. And I'm using the Euclidean norm. Great. And this is actually the operator norm, which you guys know about. And this is just a calculation. Basically, this is equal to that. So let me just get to the point. I want to show you a little bit more here. So blah, blah, blah. I'm just working out some details about this. So I finally get to this. And so then I prove my lemma that the difference of these two guys is less than or equal to L times that for L appropriately chosen as this. And then I suppose that this is true inductively. You may recall we just proved this by induction in the previous proof about 15 minutes, 20 minutes ago. And here's the induction proof it looks like here. Using the lemma, pull out that L, and that gives me this, which ends up giving me that. But the integral of s is s to the n plus 1, and this is actually an arc length integral in this context. And this took me a while to figure out because the proofs, when you look at Nagel, Saff, and Snyder, they're based on two-dimensional coordinate geometry. And this is not. So, but it all worked out. Like it took me about 3 days to come up with this. But anyway, after I did, then I was able to majorize the series, and that gave me uniform convergence, and there it is. So this is the existence and uniqueness theorem basically for A calculus, and it's proved essentially the same way as I did for you guys today in the ordinary context. So there's a little bit more to the proof. Here it is, but uniqueness and all that. The next thing I do is prove that if it's true for a first order, that was a system, by the way, a system of first order differential equations in the A calculus, then I prove that that follows then if we have a kth order differential equation in the A calculus, then, and I guess I just did, oh yeah, these are differentiable functions. Then we get existence and uniqueness for the kth order linear problem. And the proof is exactly what I just showed you guys. It's reduction of order. Same thing. Yeah. Once you prove it for a first order system, you get the kth order problem is done like so. Same, very, very reminiscent of what I already showed you guys. And past this, I just included the rest of it. I show that basically linear independence can be defined. The Wronskian still works in the A calculus. Even Abel's formula still holds in the A calculus in this sense, which goes to show you that, well, that's important to the theory of solution sets, but anyway, this is all from a paper I still need to publish. I wrote this in summer of 2016 and finished editing it, no, like 2017, Like this was done by 2017. I just I sent it to a journal. They sat on it for a year, and they're like, "This is outside our scope." And then I got busy, so I still haven't published this stupid thing. But this is the deepest thing I ever did in the A calculus by far. So anyway, that's it for today. Should I give you well anyway I'll stop recording here.